Hey, what is going on? Sec Plus preppers, CISSP wannabes, you guys trying to get ready for these exams. Taking a little break from doing my questions because I got a comment the other day where somebody went in and said, hey, Colin, can you explain a little bit more about firewall types and firewall generations and stuff like that? So Edelson Silva, thank you for the question. So what I want to do is endeavor to answer that for you guys today. I'm going to teeter on more information than you need, but I want you to understand why things are what they are, and that's going to help you when it comes exam time, depending upon the way they want to go in and ask you these questions. But what Edelson went in and asked me was really three things. One was, can you explain the firewall generations, what all that stuff's about? Two, can you clarify the different types of firewalls? And three, which of the firewalls is most secure? So let's go ahead and get right into that. First things first, we can break firewalls down into a couple different types. We have packet filtering firewalls or packet filtering routers. We have stateful firewalls. And then we have circuit level gateways or circuit level firewalls, depending on how you want to say that. And then there's application level firewalls. Now, those are broad notions of what firewalls are. The couple things that you got to keep in mind with this is that firewall technologies have evolved a lot over the past 20 some years, and rarely are you going to find just one type of quote unquote firewall within a device. I don't care whether it's an integrated component into a router, whether it's a standalone device, or whether it's a blade that goes into a switch, whatever it is. If it's got some sort of firewalling capacity, it's very common these days for firewalls to be able to do a lot of different things. So it's, your firewall can be a stateful packet filtering router, or it can be in which case is a firewall. But it can also go in and be application layer firewall, which is going to go in and do a lot of different stuff, which includes a lot of the other firewall components. So I want you to take these more as concepts, things that need to be achieved or can be achieved with firewalling, not necessarily specific implementations of a firewall. Vendors are doing constantly crazier and cooler stuff with firewall technologies to go in and help make networks more secure. What we need to do is understand exactly what they're doing under the hood. The first thing, if I just kind of jump backwards a little bit here, if we go in and address this whole firewall generations question, okay, nobody cares outside of an exam what generation of firewall it is, unless you're talking about the history of firewalls. Where did firewalls start? How did firewalls evolve? All that stuff matters because it's kind of, where we came from in the world we live in. And we call these things first generation, second generation, third generation firewalls just to sort of help illustrate the chronology of how firewalls developed. I don't really foresee you ever sitting in a meeting going, oh, we really need a first generation firewall in this circumstance and a third generation firewall over here. No, nobody talks like that. At least nobody I've ever encountered talks like that. So we need it academically from an exam perspective to know that first generation firewalls are packet filtering routers, and second generation firewalls are stateful filters, and third generation firewalls are application gateways. And yeah, we need to know those things come exam time, but beyond storing it somewhere in some back cache that you got in your brain, I don't really think you're going to need it. So I sincerely hope, and I'll kind of reiterate it as we go through, that just kind of puts that whole firewall thing to bed. First generation firewalls are packet filtering routers, second generation firewalls are stateful firewalls, and third generation firewalls are application layer or application level gateways. So let's go in and talk more about exactly what that means. So packet filtering routers. All this stuff that's on this slide, you can download it in the links below. It's all there for you. But a packet filtering router is a first generation firewall. It is the simplest of the firewalls, and it is also the first, which is why it's called first generation firewall. A packet filtering router is nothing more than a router with an access control list. Okay, that's as simple as it gets. The access control list, however, is kind of limited in terms of what it can do. Okay, it looks at the source and or destination IP address. It can look at the protocol that's in use, whether it's IP or even IPX, if we were kicking it old school that way, IP version 6. So it can look at the protocol that's in use. It can also look at the next layer of protocol that's in use. For instance, TCP, UDP, GRE, ICMP, etc. So it has the capacity to go in and identify protocols and permit or deny them based upon the protocol that's in use. If you're looking at IP addresses, source and or destination IP address, you can look at where the traffic is coming from based on its IP address, and you can look at where the traffic is going to based on its IP address. What you can then do is permit or deny based on either one of those criteria or both. They can get a little more granular depending upon the particular protocol that you're trying to inspect. For instance, with ICMP is comprised of a whole series of type and code values. Whether it's it's like a good old-fashioned ping message, which is ICMP echo request and echo reply. It can identify those. It can identify packet too big. It can identify network unreachable, protocol unreachable, port unreachable, and most of the other ICMP message types that you would think of that are out there. So it's not just about going in and saying IP is permitted or IP is denied. You can be granular. You can be specific and say echo request and echo reply are permitted, but all the other ICMP traffic is denied, if that's what you wanted to say. But you have that capacity to do that. It can also go in and look at things like DSCP for quality of service related stuff. If you have certain values that are set, it can go in and identify those. In fact, that's not uncommon. That's one of the ways that we would go in and do that to give a level of precedence to traffic to make sure that it has the quality of service that it needs as it traverses the network. Now, why do we like packet filtering routers? Well, there's several reasons. One is that they're cheap, comparatively speaking. They are fast, but that speed actually comes with an extra cost later on that we'll see. They're also pretty much integrated. If you have a router or if you have a layer 3 switch, the likelihood of it not having ACL capabilities built into it is pretty small. So we see this kind of functionality in huge numbers of devices, from wireless access points to layer 3 switches to regular good old-fashioned routers. And so on. So it's very, very, very common, been around forever, very well understood. Problems. One, the biggest problem is that somebody who's motivated can circumvent them. They are not insurmountable. Now, they're going to keep the average person from doing things that you don't want them to do. But if somebody's got sufficient motive, opportunity, and means, then they're very easily going to bypass this. And I'll show you exactly what I mean here in a second. The other big thing with packet filtering routers or packet filtering firewalls, first generation firewalls, is that they look at each packet as if it was a unique entity. No other information is relevant or pertinent. When the packet comes in, the packet filtering firewall looks at it, makes a decision based upon its rule set, and either permits or denies it. And then it moves on to the next packet. And there's no memory of the packet that came before. And so as packets are coming in, the decision is made on them one by one, with absolutely no consideration for anything that came before it. Now, as you'll see when we talk about the other package types or other firewall types, that's actually a problem. So there's a better way. For that reason, you could call them stateless firewalls, but nobody actually really uses that term. Every now and then I'll see it get mentioned, a stateless firewall or something on the internet. But if you just want to try and confuse people, then call it a stateless firewall. If you want to sound cool in a meeting or something like that. They can also have problems with fragmentation. We don't need to worry about getting into the details on that in this particular video, but fragmentation can be problematic for packet filters if they're trying to inspect certain kinds of information. And if I had to give them the single biggest problem that they have, is that they don't have any capacity to look at the payload. And in this day and age, when it comes to firewalling, it comes to protecting your network, looking at the payload is something that is oftentimes very high on people's list of priorities. And just a regular old packet router can't do it. Because it is so comparatively easy to circumvent, and because it maintains no concept of state, and because it has no capacity to go in and inspect the application layer payload, the stateless or packet filtering router is considered to be the least secure form of firewalling. And again, it's sort of the first foray that we had into the world of firewalling from a networking perspective. And so it sort of makes sense that as time goes by, it's going to also be considered to be the least secure of them. That is not meant to imply at all that packet filtering routers are not good, that they don't have a place. They just don't really have a place at the edge of your network protecting yourself from all the creepy crawlies on the internet. Using packet filtering routers or packet filtering firewalls on your internal network for specific purposes is actually very common, very helpful. And even if we weren't going to use them to control the actual flow of traffic, the whole idea of packet filtering or access control lists on routers provide a lot of other services beyond the scope of what we need to talk about today, but they do have a place in the world. I don't take it that means that they don't work at all, because they do. They just don't work really when it comes to protecting ourselves from the internet. So what I want to do is I want to illustrate to you the basics of how these things work and then show you how an attacker is going to get around one. Okay. Now this ACL right here is a simple ACL for that you might find on a Cisco router. Now in this case, there's actually two access control lists. One access control list is meant to control the flow of traffic trying to leave a trusted network, and the other access control list is going to try and control the flow of traffic as it comes back into the network. So these are the two ACLs that we're going to go and make use of. And let me go ahead and illustrate for you in the actual scenario that we have set up. So I've gone in and I've built this little network here where on the left-hand side, we have two computers which we're considering to be trusted. There's an Ubuntu computer and there's a Windows 7 computer, and they're all on the 44.44.44.0 network. Okay. Over on the right-hand side, I have two computers, one of which is just meant to illustrate a web server that might be on the public internet. It's just a regular old everyday web server like any that you might go to in terms of a website. And then there's a computer that we're going to leverage as the attacker in the scenario to go in and show you what's up. So I'm actually not, for this packet filtering part, I'm not going to use this Ubuntu Linux computer. I'm just going to focus on the Windows 7 computer. And just to really quickly illustrate some things, right now there's no security setup whatsoever. This router that's sitting in the middle is just a straight router. His job is to route packets back and forth between these two different networks. And so if we go to the Windows 7 computer, okay, and we open a command prompt, okay, we can see that his IP address is 44.44.44.88. Okay, this IP address right here. And this web server out here is at 100, 100, 100, 100. Okay, so if we open our web browser and we point to 100, 100, 100, 100, we get a web page that comes up. Awesome. So that shows me right there that traffic is flowing from this guy right here over to this web server, and it's going through this router. Okay, and if we look at our connections, just a couple things that are important for us to go in and see. If we look at the status of the connection on this computer, we can see that there is a connection from the local computer going to the remote web server. Now, the things that I want you to make note of here and that are important is the ports that the traffic came from, in this case, is 49,166. What matters to us most is that it's a port greater than 1024. Now, it's actually an ephemeral port, and what the ephemeral port ranges are can vary from one operating system to another. But this port was dynamically selected for the node when it established the connection. It's going to be used for the duration of this connection, and then it's going to be discarded, only to be reused later on by some other protocol or application. The foreign address, notice that we went to 100, 100, 100, 100. And the destination port was 80, which is the standard port that web servers listen on. So that's not particularly surprising. Now, this connection is probably timed out by now. Nope, it's still there. Okay. It's on the process of timing out. But if I come back in and I refresh my browser, or actually better still, I'll close my browser, and then we'll reopen the connection. Okay. So the web page is back up again. And now if we look at netstat again, excuse me. Notice that we now have a new connection. This one now is using port 49171, so a new ephemeral port was created, and then we're still going to port 80. Okay, so that's normal. That looks right. Everything seems to be okay. Okay. Now the other problem that we have here is because this is just routing. In this scenario, just so you know, this Windows 7 client has some folders shared out that I went in and shared out before I started making this video. Plus, it also has remote desktop enabled so that remote desktop connections can be established to it. So if we come over here to the attacking computer, we open a terminal on this guy First off, I can do simple things like ping 88.88.88. Nope, I'm sorry. 44.44.44.88. Let's just ping it twice. Okay, so we get successful pings, and so we know we have ICMP connectivity between this attacker and this Windows 7 computer. So this guy's just doing straight up routing there. And if we come back and do something like, now I'm going to cheat a little bit because I know the username and password on the Windows 7 computer. I need a 44. All I'm doing right here is I'm just asking for a list of the shares on the Windows 7 computer. And so sure enough, I come back because I know the credentials. Again, I cheated right there. But you know, I know it's a Windows 7 computer, and I can see that it's got these shares. Okay, that's great. Now, the other thing that I have support for here is remote desktop. So if we come into remote desktop, if we go to 44, 44, 44, 88, and we try and connect, notice we get a successful connection. Okay, so that all worked out well. Nice. All right, so there's no security between these two nodes. That's all I want to illustrate to you. So let's put some in. We want to create a situation where these nodes that are on the internal network want to be able to go in and access the external network, but not vice versa. If we go in, and I'm just going to keep this super simple. I want to go in right here and just focus on this right here, this list right here. I'm going to create this access control list. I'm giving it this arbitrary name called allow outbound www. Now, in order to do that, I'm going to identify UDP traffic coming from 44, 44, 44 dot anything. And if it's going, there's an error in my ACL here. I'll fix that. It's going anywhere. When the destination port is 53, then it's supposed to be permitted. Now, that particular traffic is for DNS queries. The same thing here, if you happen to be using TCP for any of your DNS query stuff, then port 53 is also allowed. This third rule right here goes in and allows port 80, which is web traffic. And the fourth rule allows SSL traffic, which I just included for completeness here. Remember that all firewalls typically, not all, but most firewalls implement the notion of an implicit deny, where your firewall, you have all your individual firewall statements, and then the very bottom of the list is a deny all. Now, not all firewall vendors do this, but a lot of them do. So that if you get to the bottom of the list of this ordered set of rules and nothing has explicitly permitted your traffic, then your traffic is going to be denied. Okay, so in general, it's regarded as sort of a best practice in firewalling, even though I've seen it, even with some big vendors, not actually honored. So I want to take this firewall rule right here, and I just want to create it in the router. I'm just going to paste it in just to be quick about it. So on this router, this is the router that's in the center here. So I'm configuring this guy right here. Okay. What I'm going to do is I'm going to go in and I'm going to create this access control list. Okay. And in order for it to actually take effect, I need to apply it to the interface. Now, I'm trying to identify traffic coming from the 4444 network going anywhere when these particular destination ports are in use. So in order to get this access control list to actually be useful for me, I want to apply it inbound on this gigabit 00 interface. So anything trying to come into this interface has to be coming from 44, 44, 44 something, going anywhere with the destination port being the ones that I've gone in and specified. Okay. So that is going to work once I go in and actually apply this access control list to the interface. Okay. So now, some interesting things that we'll see here. One is we've created some rules that limit what traffic is allowed to leave this network. So traffic leaving this network now can only go out if it's going to port 80, 443, or port 53 for both UDP and TCP. The router is now a firewall because we've put an access control list on it. And the router is now going to begin inspecting these packets as they go through to see if they meet these conditions. So for example, even though I didn't show you before, if we come over here to this Windows computer who's now bound by these firewall rules, if I try and go to the web server, I get success, and the reason I get success, and if we go look at a netstat on that, we can see that the connection is established, and the reason the connection is established is because the firewall rule let the traffic pass out. It was traffic coming from 44 dot something, going to port 80 anywhere out there. And so our rule, which is met by this particular condition right here, let that traffic leave. Okay? So that rule lets it out. Now, notice that there's no ICMP rules in this access control list. So if I try and ping 100.100.100.100, I get failures. Now, notice that the messages are coming back from 44.44.254, which is the router's IP address. So the router is denying me the ability to go in and establish this connection. Okay, we could see the same thing if we do if we open up PuTTY and we try and connect to 100.100.100.6. It won't connect. Okay. And if we look at netstat, he's trying to connect. Notice that a synchronization request has been sent, but the connection isn't establishing. And the reason for that, just so you understand, is that there's no rule that allows port 22 to go out, so this implicit deny is catching it and denying the traffic. So the only traffic that's allowed out of this network is traffic going to port 80, 443, or 53. Okay? How about traffic coming in? Okay? Traffic that's trying to come into the network is also going to run into problems normally. Okay. Now, a moment ago from this attacking computer, I had gone in and I had established an SMB connection to go in and view the list of shares that are there. If I try that command again, okay, I'm not getting a response. Okay. Now, let me show you why, so you understand. All right, so these are my connection efforts right here that I'm going in and making. So let's try this connection. So right here, I'm trying to make a connection on port 139, and it was coming from some high-level random port. Now, if we come back over to the Windows computer, what you'll see is something interesting. The connection is here. So I can't establish the connection, but when we go over and look at the Windows computer, we can see that the actual connection attempt made it into the Windows computer. Why did it make it in, but not successfully establish? The reason for that is this. There is currently no firewall rule on this interface on gig 10. So all inbound traffic is allowed to come into the router. There is also no outbound rule on gig 00 on the router. So the traffic is allowed out. So when the attacker attempts to initiate the connection inbound, the traffic comes in. It came to the Windows computer. He received it, in this case, initially on TCP port 139, and responded. However, when the response went back, the response was going to the source port that the attacker had originally selected. You do this without the watch command so we can get that to stay up. So let me try it one more time to show you. Okay, so I sent my request into port 445 into port 139, but to port 445, which is the file sharing port, it came from this port right here, 44354, which is an ephemeral port selected by the Linux computer for the establishment of this particular connection. When this Windows server responded back, it responded back, darn it, I gotta be quicker. Let's do it one more time. Get the ports there, and get the ports here. There we go. So this time I used port 44,394 going to port 445. Okay, and you'll notice right here, the connection made it into me, port 445, coming from 44,394, which is the port that we see over here, 44,394. So when this Windows computer responded back, he sent the TCP response to port 44,394, and if you look, traffic going to port 44,394 is not allowed out. So you're sitting here going, okay, well, this sounds cool. Then my internal node is protected because people from the outside can't get in. It's not actually as good as it needs to be, not yet, at least for packet filtering routers. What you want to do is actually think about this a little more, to think about, okay, traffic's going to leave because I'm going to allow it to go out, but then I only want certain kinds of traffic to come back in. For instance, I only want traffic coming from the ports that I allowed out to be able to come back in. Okay, that makes sense. And that's actually what this second ACL entry does, is it's really just a flip-flop of the two sets of rules. In this case, it says traffic coming from anywhere when the source port is 53 going to 44.44.44.anything, let it in. And that's the same thing for TCP-based DNS as well as HTTP and HTTPS. So I'm now going to create this access control list on this computer. On this router, I should say. Paste it in there. So now we have this incoming protection ACL. It's just an arbitrary name that I gave it. And in order to get this to control, I want to apply this inbound on the gig 1/0 interface. So I'm going to have an inbound ACL that controls traffic trying to leave my internal network, traffic coming into gig 00, and now I'm creating a reciprocal and complementary ACL that is going to control traffic trying to come into gig 10, which is traffic trying to come into the network. And this traffic simply says that if it came from port 80, port 443, or port 53, coming from anywhere, then it's allowed in. And that's a fairly kind of standard mentality because you don't know where anything is on the internet because web servers are too abundant. So I now need to go apply this to an interface. So if I go to my interface gig 1/0, and I apply it, it's called incoming, applied inbound. Okay, now let's watch what happens now that we've made that change. These connections should all be timed out, at least I hope they are. Yeah, so there's no connections. And over here on our Linux machine, we have some connections that are timed out, which we don't need any of that. All right. So what happens now when I try and do this SMB connection again? Okay. He immediately comes back with a failure. There's no connection attempt here. And if we come over to the Windows computer, there's no connection attempt here. The reason for this is because port 445 and port 139, which are being used by this SMB client tool, aren't allowed inbound on the gig 10 interface. And so on that external interface right here, they're not allowed in. This guy's immediately returning a reject message saying, nope, can't come in. We see the same thing with the effort that I made for remote desktop. If I went in and tried to establish a remote desktop connection to, what was it, 44.44.44.88, unable to connect, and again, the connection attempt never made it to the server. So this seems good. It seems like we've created a situation where we're allowing traffic to leave the network, and then we've created the corresponding reciprocal rules to allow back in. Now, we're supposed to be allowing port 80 back in, so let's check and make sure our Windows client can still get to the web server. And sure enough, the web server is still up. We can still get to these different pages that are on this web server. All right. And we'll notice that if we look at our netstat, we have connections because the reciprocal entries are there. There's a rule that lets traffic going out when it's going to port 80, and there's a rule that lets traffic coming back in when it's coming from port 80. Okay. So everything seems good on the surface. Here's the problem. The problem is that attackers are smart. They can configure their tools to bypass these basic rules. And this is the reason why you would never, ever, ever use a packet filtering router as your sole form of protection from resources on the internet. Okay? So what I'm going to do here is illustrate to you how an attacker can bypass this. Okay? So here's my attacking computer. All right? We've seen, just to illustrate, that when I attempt to establish a connection straight to the server, 44, oops, .88, it's rejected. Okay, so I'm going to do a little bit of trickery. I suspect, as an attacker, that traffic using port 80 is going to be allowed back in. So I'm going to run this command here where I'm going to do a very simple thing, which is get my computer to send traffic on a different port. The normal behavior of clients, all clients, whether they're Windows, Mac OS, Linux, is when they start a connection, they always start the connection from an ephemeral port, okay, which means it's a temporary port, and that temporary port is pretty much always some port greater than 1024. Again, the ephemeral port range can vary from one operating system to another, but we can safely say that it's always going to be above 1024. What this particular command is that you're looking at right here is actually going to create a local listener on the attacker's computer, and that it's going to listen on port 2222, okay, which is this part right here. I'm saying listen on port 2222. Okay. When somebody connects to that port, what I want you to do is, I don't want this to be 22, I want this to be 3389. Whoops. Try that again. Okay. I want to establish a connection, I got all kinds of errors in this, to 44, 44, 44, 88 on port 3389, but I want to source the traffic from port 80. Okay? So, whoops, I'm going to close that in. So, as the attacker, I've just created a listener on my own computer that's waiting to receive connections. In fact, if we look, we can actually see that I have a listener on port 2222. So I'm listening for inbound connections on that port. Now, if you connect to that port, what this command is going to do is it's going to actually run this command, okay, or forward to that port using that source port of 80. So let's go back to our remote desktop client. Now I want to go to 44.44.44.88, except I'm going to change the port. Oops, I'm sorry. I'm not even going to do that. I'm going to go to localhost 2222. So I'm actually going to establish a remote desktop connection to myself, the attacker, on port 2222, and he's going to forward all of it to port 3389 and source the port from 80. So let's look at this. Let's look at netstat. Okay, we have no connections. And then when I connect, lo and behold, this is actually running on my Linux computer. Now, if I look at a netstat on this machine, this is the part that should creep you out, and the reason that we don't use packet filtering routers is I've just bypassed all these firewall rules. And I did it by sourcing my traffic from port 80. Okay? So when my traffic destination was inbound on this guy going to, or coming from port 80, okay, it met the conditions of it was coming from port 80, so it was allowed in, bypassing this rule, which caused it to be delivered to this host on port 3389. Because remember, all we looked at was the source port for traffic coming in. When this guy responds, his traffic is coming from port 3389 going to port 80, which meets the inbound rule that's on this gigabit 00 interface. And so by doing this, the attacker is able to actually completely circumvent the firewall rules. So again, this is me connected in my actual Linux computer to this remote desktop window. Okay, so that's actually running here. It's not the other machine. Okay, so and this is the real danger of this. And there's basically, once I discover as an attacker that I can do this, there's not much that I can't connect to on your internal organization. Now, this example is somewhat egregious because remote desktop is running and I knew the username and password, but whether it's port scanning or connecting to Windows shares or any other kind of enumeration and subsequent attack stuff that I might want to do, I'm able to bypass your firewall rules. Okay, so the moral of the story is that you cannot defend yourself from the internet using just packet filtering routers. Okay, so in our next video, which I'll make and post right after this so you can watch them in chunks, we'll move away from packet filters as first generation firewalls and go in and look at stateful firewalls and see how stateful firewalls are going to go and help mitigate this. And then we'll also go in and inspect circuit level gateways as well as application layer firewalls and see exactly what it is that they're doing. Cool. Peace.